Okay, so that was the scan pass. So that pass is pretty quick. I said 5 minutes is generally the most. I would 5 to 10 minutes, depending on how quickly you can do stuff. Also depends on the length of the paper. Obviously, a 4-page paper is scanned faster than 15. So the next pass, I would generally say is around an hour. Might be 2, might be 45 minutes. But that's really the question we ask for the scans. How long will it take me to read and really understand this paper? Again, in doing this, right, we're going to read carefully. But we're going to ignore lots of details. We don't go through how a proof works. We don't actually analyze the statistics they talk about. We don't go into tremendous amount of detail. We want to be able to say, I have a good understanding of what this paper does and why it is important. But it's also a critical pass. We're going to go through this. We're going to note, at this point, by the way, you would be taking notes for a paper. You're going to note the assumptions and you're going to question them. It is no longer believe the author. Now it's time to doubt the author, to question them. So we're going to go in and we're going to analyze their experiments and their conclusions, right? Are those conclusions verifiable, right? We're going to analyze the figures and diagrams and illustrations, right? Are they properly labeled? You know, are there error bars? Are there things in there that I really understand what they're doing, or is it like sloppy? This is going to affect how much we're going to work things. If there are, you might mark relevant unread references. They refer to these people and they're building on their tool and I don't know what that is. Do not, during this critical read, go read it. Right? Again, it's not a depth first process. You don't like hit a, right? So if they say something comes from a paper, at this point you believe it comes from the paper and it's correct that it came from that paper and you build on it, right? You're going to question what this paper says, not what the prior work says. Prior work is another level of assumptions. So after you've done this, you should be able to summarize the key thrusts and point out likely weaknesses in the assumptions, methodology, and/or experiments. So this is literally for you doing a review. This is the first normal stage. The paper was assigned to you. There's no question of browsing or scanning it. It's like jump in and do the review. Although almost every review I do the scan first because I want to get sort of an overall lay of the land, what's going on in the paper overall, and then I go back and I read it in more detail. At this point, your third read may or may not be in order. It's actually fine to sort of read the intro, skip to the experiments, then go back and read through the methodology, so you can, and then maybe read the experiments again. We'll talk about some different things. But so the reason we're reading a paper critically is we want to really understand the problem and the proposed solutions. We want to understand the problem and its assumptions, because the difference between subproblems is often what is assumed. If I assume noise is Gaussian, I might get a very different approach than if I assume the noise is Poisson. Even though both are assumptions, right? One may or may not be better modeled in the real world, but the math and the experiments that follow after that are very different. So you got to really understand what is the problem. And oddly enough, some papers make you struggle for that. They're not very clear. Their assumptions are implicit. We'll come back to that more in the next things. Right? We want to understand the competing design approaches. It's up to them to tell me, right? Oh, it's related to this. Here's how it competes. If they don't, then the paper from a review point of view has some problems. We want to understand their evaluation methodology and how they compare to the state of the art. And if their methodology is flawed or their comparison to the state of the art is flawed, at a certain point you might say, okay, this is not worth following because what they did doesn't actually show what they claim. Right? We've said if the paper does this, it's great. But does it actually do that? It's up to them to convince you should go through this. Okay, and this is a time when, as I said, we're not going to assume the paper is correct. And this becomes true even if the paper is published in a prestigious peer-reviewed place. Just because it got published doesn't mean it's correct, let alone all the experiments were good, right? I would say 1 in 50 or 100 papers at a major conference has a fundamental flaw that was not detected during the review process. So not a lot, 1%, but hey, it's still out there. And some places it's correct, but only in a narrow sense, based on some assumptions that may or may not be valid or meaningful. So you want to be careful. But there's another reason to question it, even if it is correct. Why do you think I want you to question what's in the paper, assuming it might not be correct? What's the advantage of doing that, even if it is correct?
Forces you to think critically about the problem.
So it helps you to think critically about the problem, which is good because you have to learn to think critically about your problem too. So it's a practice. So if you think there is some flaw, and then later on you work through to see, oh, now I see it, you actually learn something about that subspace of the math or the subspace of the experimental stuff you're working on. So the fact that you think there could be a problem and you dig through it is actually really good for your own reasoning, which is the other value you get for it. So critical read may require you backtrack, fact check within the paper, jump around to evaluate the claims and items related to the paper. As I said, at this point, you're going to presume, so if the odds that a paper is wrong is 1%, the odds that a paper that was cited by them is also 1%, but maybe even less so, because then you can start looking at how well cited is the paper, what's going on. So you can check that. But for now, don't worry about digging through that. When I say backtracking, it's within the paper. Papers will more commonly have inconsistencies. They assume something here and assume something in the next section, and either of those might even seem like a reasonable assumption, as long as you don't assume them at the same time. So if I assume it's a continuous distribution, and then I assume it's atomic or discrete, I can't be both continuous and discrete, right? In either section they might be. So those are the kinds of flaws you'll actually see in lots of papers. In fact, I would say very few papers, coming back to like the proofs in the math, very few papers have algebra mistakes. They may have typos. That's not that uncommon. But the authors rarely make algebra mistakes. What they do is they make mistakes that are assumptions that shouldn't be made. They're not consistent. And those are the ones that are hard to find. Checking the algebra line to line can be useful. So these are some high-level clinical questions that to me are a hint there might be something wrong and I need to dig deeper. So if the author's been cutting corners, intentionally or unintentionally, in terms of like how they do their experiment. So we ran it this way, but we only ran it for like 10 seconds instead of 2 hours because of the computation, right? Now, if they say we only let it run for a day instead of a month, yeah, that's not really, that's maybe reasonable. But I read papers where they say, for computational reasons, we cut it off at like 10 minutes. It's like, what kind of computational reason is that? That makes no sense, right? When they're telling you that, then I start wondering, like, is there something else wrong? Right? Is there something deeper you got to dig into? Do you think it is impossible to reproduce the results? There are plenty of papers where I read where it's like, there's absolutely no way I can ever reproduce this, in which case I'm going to be very critical about this paper, because now I have to get the understanding of the paper without ever being able to test it. That's a bad place to be. Are there things problematic about their experimental setup? We'll talk a little bit more about some of those on some later slides, but lots of problems for me. A paper has experiments that can't possibly prove their claims. Now, the experiments might be fine, but the claims can't be proven from those experiments. And when there's that level of disconnect, then there's something wrong with the paper and you want to understand what's really going on. Now, in fact, when I say there's lots of problems, so provably wrong papers, maybe one in 100. Papers where there's a disconnect between the experiments and the claims, probably like 10, 15%. There's lots of them where they claim something very significant, they overclaim, given what their experiments allow them to prove. And that's a very difficult thing. Are there weird confounding factors? In our fields, there are lots of confounding factors. If I work with humans, right, human subject experiments are just plagued with all kinds of problems because my sample size has all of these difficulties, collecting the right people, getting them at the right time. When I'm dealing with computers, I can have all kinds of confounding factors. Because did I actually how did I control the environment? Is that a representative environment, right? Is the network traffic, right? So if I'm doing something on AWS, well, if they don't tell you what time of the day it was for AWS, that actually has a big effect. Because if I do it in the Pacific coast at the midday of the Pacific time zone, those computers are much more heavily loaded and there's actually much more swapping going on between processes that I don't see. Or if I do it in the Pacific at 4 a.m., there's much less demand on the machines and I get a more efficient thing. So there's literally cache effects, all these terrible things that you don't even see. That can be confounding factors, right? If the effects are large enough, they may not be important, but there are times when you have to understand what's going on, and they don't talk about it.
Is that true even when you have like a
dedicated instance?
Yeah.
Yeah, still true.
That's nice.
So less of an issue for a dedicated. So a dedicated instance means you have this machine, but what you don't get to see is what's happening to, for example, the data store, which is not your dedicated machine, right? So when you're hitting the data store, if thousands of other people are hitting it, more of an impact than if no one's hitting it. If your network traffic, right, gets congested because of network traffic. So your pure CPU stuff, if you live entirely within your machine, yes, now you don't have caching effects. They're all yours, right? But you still get disk effects and network effects. And that's the question of what are the confounding factors and what do they try and do to control for them? Or, in fact, sometimes you can't control for them. So what you do is you randomize across them. We'll talk a lot more about design later. So it's like, okay, I did it in 3 different time zones. If I ran the experiment exactly once, you can't randomize or control for the confounding factors. If I ran it 10 times in different days, I get more things. Another classic one is the benchmark that they're going to compare against. Is it realistic or artificial? It is not uncommon for papers to say, here is the state of the art, and I've compared against it. And actually, it was the state of the art 3 years ago, but it no longer is. Or they just make up a benchmark. And this is the artificial benchmarks are actually most common in papers for which it's a new problem. We'll talk about those types of papers later. No one's ever solved this problem, so I have to make up a benchmark because I'm the first one to solve it. Well, I can make up one that's actually a pretty good estimate, or I can make up one that's just like, yes, it's a benchmark, but it's really lame. We call them straw men, right? You just make one up. So, and when I see that, I want to dig a little bit deeper. Are they comparing apples and oranges, right? So I'm making some claim about how much more efficient my algorithm is in terms of the way the data structures work, and then I measure CPU wall clock time, right? There's a ton of other things, I/O, there's a whole bunch of things that are not in there. So am I comparing these? Or am I comparing one system as published in a paper where they have timing from a computer that's not the same as my timing, right? They ran it on a Pentium 4. I used an i7. Oh, look, I'm much faster, right? Those are just completely irrational things. Now, no one will tell you they did that. What they will tell you is, we're comparing against this table from that paper. And then you have to figure out what's in that paper. So there's a trick there to figure out what's going on. Are there methodological misunderstandings? Do they do things in the paper that are inconsistent with their own methodology? So we assume things are uniform random, and then we model it with the Gaussian, right? That's a methodological misunderstanding. You can't do those both at the same time. Not quite as bad as assumptions, but if they assume something is one thing and then model it mathematically with another, you have to understand what's going on. Do the numbers actually add up? Every now and then, this is mostly related to quantitative experiments, but sometimes you'll see they'll start the paper. We did this experiment with 500 samples. And then by the time you get to the experiments, there's like 120 things here, right? And of course they had these qualifications. So 500 people went in, but only 120 ended up in the experiments, right? To me, anytime somebody does that, they're trying to mislead the audience. And if they're trying to mislead me, then maybe I should dig a little deeper. Maybe there's some other things they're trying to cover up, right? So, they were honest in the fact that they got there, but sometimes they won't tell you there are 120 episodes. You go through the table, it's like, well, there's 30 in this group, so 35 in this group, and 25 in that group. It's like, where'd the 500 people go? There's only, so you have to dig through it. Are the generalizations valid? We'll come back to that. And then are the claims modest enough? These two, to me, sort of go together. Lots of papers overclaim. The more they overclaim, the more I don't trust them. Right? The more modest they are about what they're saying, it's like, okay, if that's all they're claiming, that's probably true, and I can trust them. They're not overclaiming. Otherwise, you have to dig through it. So you want to ask questions about the credentials and reputation of the author and the place of publication. This is sort of high-level questioning, right, what's going on. I question people I don't know more often than people I've read their work and I trust their work. Right? There are people who, because they're senior and because they've done really good work before, if they make a bold statement, I'm going to question my thinking, not theirs, more than somebody I've never heard of who says something to me that's like, sorry, that just can't be right, right? How much am I going to dig into my own self-beliefs? So you can think a little bit about that. Another important question is, what's the writer's purpose and the audience for whom the author is addressing? So when I'm reading a paper, when you're reading a paper critically, it's actually very different. If it's a magazine article, you don't hold them to the same standard or the same goals as a technical research paper. Right? So critically, you have to think about what's the audience they're aiming for and what am I trying to say. If they're a little bit off in addressing a broad audience, you can cut them some slack because they're trying to get it so that the average person gets it. They don't want to get the technical nuances or they can't fit in the paper. So it's very different than if they're trying to address a very technical group, and then they abuse the terminology or they get something wrong. So you want to go through that. Ask questions as you're reading. So it's an easy way to do this, right? So I don't read in paper. I'm an electronics guy. I hate paper versions. But highlight as you're reading. So this is, this is a practice part for you. As you're going through your critical reads, spend some time to make notes in the margin of the paper. It takes a little bit of time, but you'd be surprised by the time you get done, you've put them. So if you're online, highlight them and do whatever. On paper, highlight them and put some whatever. But write the annotations in the margins when you're done. Right? If the second you have a doubt, make a notation about it, because you'll be surprised after you collect enough of these, you're starting to see a pattern. There's a secondary reason that comes in. So if you make a note of what troubles you go through these papers, and you start becoming very attuned to, gee, that error that I had went away later, but I should have never had it in the first place. It's a writing problem because you got stuck on this, and then later in section 4 they fixed it, right? There's some ways of fixing that when you get to writing, but you become more attuned to it, and you may become more attuned to it in your own writing instead of, oh, I'll get to that later. Be on the lookout for assumptions will be faulty. We'll talk more about that, right? So, so if you're reading an article on computer-aided online education, and a writer favors online education because it avoids subjecting students to violence in schools, right? There's an unstated and in fact generally untrue assumption that schools are violent places, right? So when you're going through this level, you're questioning not just stated assumptions, but actually lots of unstated assumptions underlying their work. So if I'm looking at something and I'm assuming that access to main memory is 1,000 times slower than access to a local variable, right? Well, there's this thing called a cache. Yes, main memory is, but that assumes everything I do is a cache miss, right? So again, there can be all kinds of implicit assumptions that they build into their writing that you want to start looking for. So notice how the user uses the language. Do they write with positive terms or negatives? Connotations, looking at the values that the writer holds, right? If they flamboyantly denigrate and dismiss other points of view, such as a ridiculous notion or inept policies or anything that's really a strong put down of other people, again, this raises the fur on the back of my neck and makes me say, these people are aggressively trying to mislead the reader, right? And it's possible they're laughable inept policies, but there are very few that are that bad, right? And so they're trying to convey something ascientific, right? Their personal opinions by the flavor of the language. And when people do that, then you want to be a little bit more critical about what's going on, because they may be very good at leading you down a garden path and you go somewhere. Related to that would be sweeping generalizations of bias and prejudice. Wouldn't want to stay at home and have children, men love to spend Saturdays hacking code, right? These are just ludicrous ideas but people put them in their papers, and they bias the way readers feel as they're reading the papers. And you can flip this around, right? They can bias you in a very negative way, because if they make those kinds of statements, why should you trust anything these authors say, right? And at a certain level, that can be part of what's like, okay, if they think this, then I don't trust much of whatever they say. You want to look at their evidence and that is adequate and accurate. For example, if they're making generalizations about programming skills of Chinese students, but it's based on a study of only 10, then they've pretty much shown I don't know how to do good experiments because I made a gross generalization from a very small population. Can I do something with a population of 10? Absolutely. Can I make a broad statement? No. Right? My population is way too small to do this, right? And you'd be surprised, and I've used things a little bit farther from everyone so that I don't have to, I'm not trying to pick up papers, right? These examples are really obvious to you, right? As opposed to, but you'll see something similar in technical papers where it's something that you have to dig a little bit to sort of say, okay, I ran my program 3 times and it's 5% faster than this other program. At which point I'll say, okay, and if your program is 5% better on those, how about on these 5 over here, these 5, right? Different runs of your programs, we'll get into statistics later and we'll see. That's a very common problem. People like to generalize from a small number of examples, and that's often a problem. So some critical questions, I'm going to spend a lot of time on these. Is the problem carefully stated, formulated? If you can't find a very formal statement of the problem, then the paper isn't very clear about what it's solving, then how can you answer, did they solve it? Right? So I like to have papers that have a pretty carefully formulated definition of what their problem is. And then once I have it carefully formulated, you can ask, is it a meaningful, real problem? There are lots of papers where you read them and it's like, gee, if the world was like that, it would be interesting, but that's not our world, right? The problem isn't real. Now, you can't just say you're going to ignore a paper because it's not a real problem. It might be abstract, but that abstraction might apply across many problems. So it doesn't have to solve, it doesn't have to be in the context of a real problem, but maybe it could be applied to a real problem. Right? So you have to balance what that is. Is it the right problem formulation in terms of the formulation versus the description? They might actually say, here's the problem I want to solve, and then they formalize it in a way that disconnects between the two. Again, when papers try and get mathematically precise, they often run into this problem. So somebody's doing GAN work. Is that you're doing GAN, right? So, in some of the GAN papers, they say we're going to build this general neural network, but they never formally define, in terms of their formulation, right? They're going to say, well, it has this discriminator. Okay, it's a discriminator, but if they don't define formally what the inputs are in the training on it, you get something which is like a fuzzy mess of exactly what is the problem. Even though the underlying problem, what they wanted to do, might have been sort of clearly defined formally, it's not connected to the actual original problem. Right? And it's easy to get things that in the machine learning space where what we say the problem is and what the problem turns out to be are actually different. What's novel about the problem formulation? We'll come back when we start talking about writing, right? But there are papers that are solving a well-known problem better than other people have. And there are other papers that are saying, here's a novel formulation. Well, it might have been novel to say, I'm going to store my encrypted data as RGB channels in an image, right? But is that actually meaningful, right? What well-known problems are related to this, right? Encryption is about encryption. It's not about how I store them, right? And so even though the paper said it's about text versus binary in the way they store, text versus RGB, what it probably was in their speed difference is if I do I/O as a binary blob, it's faster than if I do it as an ASCII blob. Okay, that's already well known. There's a whole bunch of problems that are related to that in terms of how I do I/O. How's it related to your problem? Are there simple solutions the authors do not seem to have considered? This to me is another classic problem, and this one can be useful for your own insights. So, was there a simple way of solving this problem rather than this convoluted, right? And maybe the reason to think about that is that maybe that simple problem was overlooked by them, or maybe they chose to make it complicated so they could say they did something novel. But if I could solve it with a simple way, right, it might not be publishable. Maybe it would be. Depends on what it is. But if they don't compare against it, they don't talk about that, then it's also a limitation of the way the paper is coming from. The other reason that's useful is that sometimes when you think there's a simple solution and there's not, it's a mistake in your thought process. So as you think through, oh, I think that could solve it, and then you work through, it's like, oh no, it doesn't solve it for this reason. You improve your own thinking. So can you make a list of assumptions explicit and importantly implicit about the technique? This is one where there's a lot of places where the implicit assumptions, to find them, you can really look at pretty much every matrix, every divide. So what's implicit if I divide into numbers? I'm not dividing by zero, right? It's a bad thing to do, right? So matrix operations, right? If I have a matrix operation, right, depending on what that operation is, right, I probably have to assume, if I want to invert a matrix, I have to assume it's invertible. If I'm going to multiply by a matrix, then I might also be assuming that the matrix is a full rank. Otherwise, I can throw away subspaces, right? There's a bunch of things that show up. If I'm going to do functional inversion, minimization, maximization. So if I do minimization or maximization, what do I assume? Maybe, maybe not, depending on how I solve it.
A lot of times that there's not a local min-max.
Right, so the question is, can I, if I assume there's a minimum, is there a unique minimum, right? Or are there multiple of them? And is there a local minimum or global minimum, right? Can I get to there, right? So if I find the local minimum, that may not be the minimum of the problem. So all of those are assumptions. Anytime you see those things, those are the classic places where people sort of mess up. They go find a local minimum instead of the global minimum, but their proofs were about, we find the minimum value, and it's like, no, you don't, right? What else could be interesting about if they make these assumptions implicitly? What else might be valuable for you as a reader if you can figure out they've made these implicit assumptions?
Well, as an engineer, sometimes when we make implicit assumptions, those lead to other assumptions that you've made in order to make those assumptions true.
Right. So one is, in fact, this assumption may be true, right? The matrix may always be invertible because of something you didn't think about yet. So you'll learn more about what they're actually doing. Okay. The other possibility is the assumption is wrong. What else might you learn if the assumption is wrong? Well, so you may or may not figure out the right assumptions. But let's say you have this published paper, and they made these two assumptions, and those assumptions, in your mind, are wrong. What else might happen?
Change the conclusions.
So, yeah, mess up the paper. Well, what might you do?
Rewrite the paper with the right assumptions.
Right. So you might publish a new paper, which is, oh look, that paper said these things, which is wrong. We fix those things. We apply this. Now we get a better solution, right? When you can find flaws in existing papers, And this is the kind of thing, like paper lazy get published with weak or bad assumptions, right? Because they can say, well, you know, it's in general true that this matrix is invertible. Well, if the matrix is not invertible 5% of the time, you might still get another paper out of, we do this, we make it well conditioned, we do this, we get some approximation. So even if the assumption is true most of the time, if there's enough interest in those other times, you can get a new paper out of it, which is another useful thing. What are limitations to solution, including limitations other than might have noticed or clearly admitted, right? So if the solution is fine as long as everything fits into RAM, right? Because of the way the computations work, right? Then what you've really figured out is there's a limitation to the solution, which is how big a problem can they solve, right? And oddly enough, I've seen plenty of papers where they assume we're going to scale this up to really big problems. They only test it on small ones, and you realize it'll never scale up because of that, right? So it limits where the paper can go. And then, is the logic of the paper clear, justifiable, given the assumptions, or is there a flaw in the reasoning? Well, I said very people will have algebra mistakes. There's lots of flaws in the reasoning where people make logical assumptions, where you say, well, if A, then B, right? And then they assume B is true even though they don't know A is true, right? Or inversely, since B is true, they presume A is true, right? But if A, then B does not mean anything about the truth of A. If B is true, A may still be false because there may be other ways, right? So you have to understand where the reason's going. They don't write it in nice simple formulas like that, but you can fix them. Do all the pieces of the work fit together logically? Do they sort of have theorems supported, proofs given, cited, right? At this point, I'm not really saying are their proofs correct. There is a place in critical reading for papers that have theorems. There's a point to check their theorems, though normally that's during the review process, not during after they're published. So if they cited a theorem, this one becomes interesting because sometimes they'll cite a theorem, and I've seen this more and more today, where people cite stuff in archive as a proof. It's like, I'm sorry, that proof is not proven, right? That's an archive proof. The other is they'll cite something, but they won't quite use the theorem correctly. That's the biggest problem I actually see. Is like you go read the original citation, and it's not what they said it was, right? They misunderstood, and now they say, well, because of that, we can apply this. So has the right theorem been proven, or did they get the wrong theorem for what they wanted? If the authors present data, did they gather the right data to substantiate their arguments? They appear to gather it the correct manner. So this is a big problem in computer science papers where we don't collect the right data to match our claims. They did something, they collected data, intrusion detection. I can collect a whole bunch of stuff, but if I was measuring it and there wasn't an attack, then it's not a measure of an attack. If I measured it on a Sunday, it may not actually be relevant to normal traffic, right? So it depends on when you're measuring. There's a whole bunch of things that can go in the way in which I collect data. And then, do they have enough data to make a statistically sound decision? Coming back to like the size of data sets are very important. Very few papers, to my sad dismay, I would say maybe 1 in 10 papers in a computer science conference or journal will actually have enough data to draw a statistical conclusion. Actually, I should take that back. I'd say 10% understand and use the data to draw a statistical conclusion. Lots of them have enough data, but don't use it in a way that lets them draw a conclusion. And we'll come back to statistics later in the semester, so we'll get into a lot of that.
And we don't really do, within computer science, we don't really do like power studies and these kinds of things traditionally, do we?
No, power studies.
More psychological behavioral science.
So power studies are important psychological because there's such a variation as what's going on. So most things in computer science, we actually have enough regularity in our world, but more importantly, enough volume of data. We rarely have to worry too much about the power.
Right.
But the question is, do we actually design the experiment and run the experiment in such a way to collect random variations?
We're not selecting certain types of data too.
Right. Well, and the most common thing is like people report on 1 run or 2 runs, right? So the answer to that is the power is nothing. Like, you really can't draw much of a conclusion because you haven't even measured enough background to get to the point, right? And oddly enough, almost anybody who gets to the point of measuring statistics instantly gets the power they want because it's not hard once you set it up. It's just no. Here's you see my average performance is better than this, right? Yeah. So did they interpret their data in a reasonable manner? Would other data be more compelling? Again, this is coming back to how do I make the paper? How do I understand what the data in the paper is, and are they using it well? Would other data be more compelling? So if they ran an experiment, and you're like, well, why did they use that data? They should have used this data. So why do you think that's important when you're critically reading a paper if you think they should have used something else?
One, it invites another paper,
Yep,
as
so-
we talked about before, but the other piece is that pre-selection type of stuff. So
So-
I'm pre-selecting data that's going to support my conclusions and my process. That's not very interesting. It's a very narrow solution.
Right. So in fact, there are papers in my field for sure, but I'm sure papers across most of computer science where people do what we call data set shopping. Right? I have an algorithm. I will find a data set for which my algorithm is better than that algorithm. It may not be true for other data sets, but there is one data set for which it is true. Right? And so when people choose weird data and or they represent it in a weird way, you sort of like, why did they do that? And it's like, this would have been the natural data to use. So if they didn't, then you have to question yourself. Did they do it on that data and then choose not to report it because they don't beat the state of the art of that data? And there are plenty of papers that show up that way. Did they compare with the actual state of the art, right? This is another classic one. You say in your paper, we compare with this, which is state of the art. And it might be state of the art on that problem over there, but not necessarily on your problem. And so maybe it's not the real state of the art. And then this gets to be a little tricky as you're pushing the state of the art changing on a rapid basis, right? It literally could have been the state of the art when this paper was submitted, right? But the review process for the paper took 1.5 years, and by the time it came out, it was not. But it's still interesting to know, right? If it's like, well, I've seen that algorithm is much better than this one, then this paper is not very valuable for me, right? So this question is because if it's not the actual state of the art, you definitely want to build on this. You want to figure out who's got the actual state of the art performance and figure out what's going on.
Two questions.
Yeah.
So let's say somebody did not do data set shopping and like use one data set for his or her experiment and the results were not that promising, but still they made a good story
Mm-hmm.
in the paper. So how much of a weight does that have?
So they have a data set. So actually, if the data set is the right data set, and they're still good but not state of the art, is that what you're saying, or they chose a bad data set?
They chose
A data set, a common data set.
Yeah, they didn't do shopping.
Okay.
And they have like decent, comparison with the state of the art.
So then the question will be, what was the paper's claim? If the paper's claim we are better than things, then they have to beat them, right? If the paper's claim is here's another way of getting near state-of-the-art performance at half the cost, well, then they might still have gotten it, right? The question is, what are they claiming, and do their experiments support their claims? Right? You don't have to beat the state-of-the-art on the measures the state-of-the-art used. You can have a new measure. Look, I've got better privacy, right? What did I give up to get privacy and get close to that result? I have a fingerprint algorithm, right? It was half as good as the state-of-the-art in accuracy, but it had all this privacy properties, right? That's a trade-off you could be willing to get. So there's got to be some dimension at which they beat the state-of-the-art. Otherwise, why do you care?
Sometimes a novel solution, if it's more generalizable, is interesting as well.
It can be. Yeah. So the fact that it's novel, but if it's novel and an 80% solution on 5 or 6 problems, it may still. I mean, some people will find it interesting. Personally, my view is like until it actually solves in some dimension some problem, right? Then why do I care? Now, if what you really want is look, I have a small code base because I can use the same tool 8 times. Then that's actually interesting. But you found the dimension, and it'll be your job as a researcher to find the dimension in which you beat other people. And we'll come back to that. But yeah, that's not the same as data set shopping. If they're not beating the state of the art, but they're close, hopefully there's some other dimension they're saying is important to us, and we're doing well at that.
Like novelty would be.
No, novel. So I'll be very careful. Lots of conferences will say novelty is really important. Right? NSF will say novelty is really important. So there are people for whom the fact that it's novel is an important enough factor. To me, never. I don't care if it's novel. I care if it's good. Right? If it's not better than something else, then why? So it's not my job to figure out how to use your novel thing. It's your job to figure out how to show me your novel thing is better than the previous thing. Right? We're a synthetic field. I can always do something different. Right? I can make mine use, instead of RGB, I'm going to do RYF, right? Where I make up something, right? So what, right? It doesn't matter what I do that's novel. only is it better in some way that somebody cares about. Now, that's my view about how to do good research. Right? You can always publish things someplace that are novel. Right? And I'll tell you, if you can find a way to describe it as novel, you increase your chances of publishing. We'll get back to that, right? So, but to me, that's the author's job to figure out what the novelty is good for. Not my job. Another classic problem is the same data used for training and testing. And especially as people who are not in machine learning start applying machine learning, you will see tons of papers that don't do the machine learning properly. It's pretty simple. If you train and test on the same data, you cheat, right? Because I've trained on the test data, right?
What about the ways that they do cross-validation? Because some people will be like, I do 5-fold cross-validation, and other people will be like, I did 70-30, it was good enough.
So if you do 5-fold validation, if it's proper validation done properly, that's always acceptable. The question is what statistical power it has, right? If they do 70-30 train and test rate with no validation, that's okay. They just can't draw any statistics from it. So you have to be very careful how to interpret that. We'll talk a little bit more when we get to the statistics side, right? But this is one where I see all the time where people say, well, the papers don't say, right? And in my view, when most papers don't say, I trained on this data and I tested on that data, it's because they trained and tested on this data. There's another one which is actually more subtle and, in fact, unfortunately far more common, which is, were parameters selected to improve the test results? So people will run, I've got like 8 parameters. I will choose the parameters that give me the best performance on the test result. Now, that's not quite the same as training my entire model, but it's the same. Because what I really did is I ran my model and I changed a common thing for people doing machine learning or even model selections in machine learning. I'll do a hyperparameter search, right? I will do a grid search. I will try every value of alpha, beta, and gamma, and I will tell you, for this value of alpha, beta, and gamma, I beat the state of the art. Now, for almost every other value, I don't beat the state of the art, but that's okay, right? No, that's not okay. If you choose your parameters on the test data, you get something that is statistically not meaningful because you optimize on the test data. There is no variation on that, right? So it's especially bad now. If the proper way.
There's a logic behind selecting those particular hyperparameters.
So if there's a logic behind them, and so this is when I'm reading a paper, right? So they say I chose this parameter for this reason, this parameter for that reason, right? I would expect them to do a study. So if the results are stable around that region, right? So that if I look at the performance of the curve and it looks like this, right? And their theory told them to put something in the middle. Hey, they're showing their theory about why the choose is right? If their theory says it's this value and you look at it and it's like this, and it's like, okay, the theory doesn't predict that it's going to have that kind of fall off it.
Right.
So can you? But you don't choose them on the test data. You evaluate over test data, and then you understand how it relates to your theory. But there's a lot of papers where if you change those parameters even a little bit, they don't beat the state of the art. Right? And they'll talk, even if they do statistics sometimes, they'll do this, which I find very annoying. And by the way, full disclosure, I have papers that have done this. I have papers that have done training on the test data, not intentionally. That's like, you literally had a bug in the code that let the test data leak through to the training data, right? And some student didn't notice it, and like years later, I actually published a retraction of the paper because we did that. And like later on, we couldn't reproduce our own results, and it's like, what's going on? We coded this from scratch. How can we not? And then we eventually found the bug in the original code. So it's not always intentional, but parameters on this to improve the test results, right? It is a common experimental paradigm. We actually have one paper where we said, we did this experiment just like everyone else did, and we beat them at that result. But that's cheating. So we ran another experiment. But of course now we can't compare against anyone else because we don't have their code. And so you follow along because once this becomes the selected paradigm for some experiment, you sort of have to do it. And then you look at, well, here's how much I lost, right? I don't always beat them with this. And unfortunately, some reviewers will beat you up because you didn't beat state of the art. It's like, that was state of the art cheating results versus our non-cheating results, but you have to go through. So do the results actually show what they wanted them to do? And on what dimensionality did they advance the state of the art? Right? This is important to me, right? You don't have to beat them on every dimension, but it's the author's job to tell me that dimension where they do win, right? Not leave it as a vague thing for us to get to. So, why don't we take a 5-minute break and we'll get back to the next pass right after this.
I start talking too much, just tell me to shut up. It usually works.
Oh, and just start calling out other people.
Or throw stuff at me. I don't know.
So Heather, are you working remotely someplace? I remember I said you were like working like Nebraska or something?
I work for the Nebraska Applied Research Institute. But there were some issues with their EECS department. I was originally from Florida, and I went out to Nebraska because I was going to do dual research with the university and work towards my PhD. But because we're an applied research institute and we're not directly related with the College of EECS, they saw us as a competitor for funding. And so I began to have issues with my committee advisor and my board, so I left. And because my workplace can't control office politics, they're like, all right, we're going to have you go remote.
Go find another PhD program and keep working for us?
Yeah. We know you're going to be valuable, so we're going to allow you to do remote in hopes that you come back and we can hire you to do more full-time stuff.
Well, that's good that they're understanding.
I appreciate their understanding, yes. It's nice to have a mostly full-time, like 75% full-time job while I'm doing work. And it's actually involved with research. Because I tried doing threat intel and doing my master's at the same time. Very conflicting priorities.
Yeah, if you can get your work and your research to closely align, it's even better.
It's hard. There's just, the incentive structure is off, frankly.
Yeah. But it's not in their incentive. You have to find those
You have
two
to
things.
incentivize them to want to work with you, yes. The incentives aren't naturally there.
But if you help them get the funding, so if you start looking for funding opportunities where your advisor and
I
them-
already got them a funding avenue, which is probably why they're already amenable to this. Otherwise, they might not be as forthcoming.
But if you can find, if you can find the next one where
Fair.
your research and that can be like, that's what you want to do. Right?
Right now, I'm trying to document the research that I did for them, but we're having issues at the IRB level because the university is dragging their feet. Like, the range is complete, we have an entire way to do data and people who want to sit for IRB. But then the IRB, it's like, we don't understand what you're doing because it's cybersecurity human factors research, which we've never seen before. So it's like, they're dragging their feet. This is like the third month in a row.
Have you gone to the IRB meeting?
This is through Nebraska, so
Oh,
totally different.
gotcha. Yep.
Context.
Yep.
Although-
UCCS seems to be kind of easy.
They're quite reasonable.
Yeah.
So I've had much of it.
Yeah,
But-
University of Nebraska goes through, they have like a full research medical center, so we have to go through UNMC's IRB
Nice.
process,
Nice.
which
Yeah.
is why it's been so.
Although
tedious.
surprisingly, because we've also done stuff with NHS in my previous university, I did stuff with medical schools. It was actually much easier to get through the medical schools IRBs.
I wish I had the same
Well,
experience.
so, but by basically explaining to them, it's like, here is our IRB process, right? Here are the risks to the humans. If you start with like, here's what can happen, right? Well,
Confidentiality.
well, no,
Sudden instant death.
we start with things that's like, right, they can trip getting in or out of the chair, right? At a certain level,
It gets ridiculous.
It's like,
Ad
what are you
nauseam.
talking about? It's like, well, that's actually probably a greater risk, right? They could be like, get hurt walking into the building than any of the physical harm that can come during our experiment, right? And then what's the other thing? It's like, the most common risk is they know they were in our experiment, right? That's actually the biggest risk. So we do lots of stuff where we try and get out of, like, no, this is exempt, right? So you can't, I've been in.
It's helpful to be exempt. The problem for us seems to be like they're not familiar with cybersecurity research. So we're coming up along issues like, why aren't you including pregnant women in your study? Well, that doesn't actually affect pregnant women at all, so why would we have them in our study? They're like, but you need to include this. No, we don't.
That's weird.
So,
It's a different system.
The
and
include
I
the,
can't
the
say
actually,
that they're
out of the
that.
inclusion criterion is one that we did face problems with in medical schools, and so the answer is like so. Part of it is our study does not consider the impact of this, right?
It doesn't,
Right.
yeah.
But if you call it out, then
If you
should be
didn't
okay.
say that up front, so
Fair.
these people, that's why like they're pedantic. You just say, here's all their things. Like we don't do this, we don't do that, we don't do this. Like here are the risks of the chairs. Like to us, it was like it's like stupid, but they're like, what's the most significant physical risk? It's like falling down. I don't know. Eye strain. Right? You come up with one or
Eye
two things.
strain.
That was another one we used. It's like yes, because they have to look at the computer for an hour. They could get carpal tunnel for the half an hour of use or eye strain. And so you have to look at the IRB as really simple. The goal of the IRB is to cover their behinds, right? So
Right.
if you don't make it easy for them, they're not going to. Anytime they can invent a risk, like oh no, it's not covered. It's like because it's not slowing them down to make you wait another month.
That's true. No, that's true.
So, and the other is, Keith's comment is right. If you can actually attend, even by video, you'd be surprised when they start to understand what's going on because they're like, I'm reading this paper, I know what's going on. They ask you questions, they might actually feel a whole lot more comfortable. It's like, yes, you really do know what's going on, you just don't know how to do the IRB paperwork, but we'll help you through that, as opposed to, we think you're trying to get around something. Right?
It's much easier to explain that you're an idiot and you don't understand their process, and if they could please help you.
Oh, we've been on the phone with them, with their coordinators, so it's like they know. They're just
You're
inept.
doing good.
Like I can't control their ineptness.
So is there a reason you're not at least expedited as opposed to?
Oh, it's expedited. It's just they're still
3 months is expedited, okay.
Yeah.
Because then you don't have to go to the, well then you're not tied to the committee meetings to get stuff done. But.
Well, yeah, we're like I think this is our third review. Like, so we keep going through cycles of review, and instead of being like, hey, you guys are dumb and filling out the IRB paperwork, they're like, here is a formal letter with all of your mistakes.
Mhm.
Good luck fixing them. We're not going to tell you how. Yes. It's been fun.
If it makes you feel better, checking it over and you get something completely approved.
Don't tell me that.
The IRB only took about, one or two tries. It was
Okay.
everything after IRB then.
I can tell you, we can exchange some horror
Horror
stories.
stories,
So
yeah.
I can just tell you, do not proceed on the research without the IRB approval, because by far the worst thing I've ever had happen was a student who lost a third of his thesis, right, and could not publish it because they decided he continued without proper IRB authorization.
And you can't do that federally. You have to have authorization first.
Yep. So you can't start any experimental data collection, and the fact that it showed up like 3 or 4 weeks into his data collection, the whole thing was tainted. Throw it all away. Go start that part of your research over again. Because especially when you have a medical school involved, they don't mess around, right? It's like,
Right.
yeah, it's like, what's the harm here? It's like, they decide we violated that, right? All of our federal
other
medical grants, right? Yeah.
research
Right.
is a risk. Yeah. Oh, I get it.
Okay, so now on to the fourth pass of your reading. This is the creative read. This is both, for me, the most fun, and for many students, the most difficult. And maybe it's just because of who they are, but reading critically for most people comes out to be pretty easy. I want to poke fun at people, I want to find flaws, and maybe that's not you. If you're the upbeat, positive person, this will be easier for you. But reading creatively involves sort of creative thinking, right? So we already started with the most important question. What is the novelty of this paper, right? That's sort of creative, but they probably already told you that. The real question is, what new directions does this paper open up for me? Right? What can I do with this paper I could not do beforehand? And that's a important direction. So what are the good ideas of the papers? Do they have other extensions or applications the authors might not have thought of? That can be generalized further. As you found the critical limitations of a paper, they often suggest ways they could be generalized and made better. But sometimes it's like, oh look, they applied this to intrusion detection on a vehicle network. Can I apply that to intrusion detection on my IoT things? Right? Whatever the range is, right? So are there extensions you could be looking at? I will give you a word of caution. Don't presume the authors have not asked themselves this question, right? That you're the first one to say, oh, I could apply it over here. The authors might have thought about that too. And but they might not. So how might there be something that the authors have thought of that they aren't going to follow up on?
It's not an area of their interest.
It's not an area that's in their interest, so that's a possibility. There's actually a telltale sign for many papers, which is it's not in the paper itself, you have to do a little bit of digging. But what do you think happens to the person who's just finished their PhD? What are the chance they actually follow through on the work they just did?
Probably about -3%.
Yeah, so not very often does someone who's graduating follow that work directly. And oddly enough, in their lab, the advisor probably doesn't have another student lined up to jump on that right away. They often have so you can sort of get a feel, so like, especially if you get to talk to people at conference, but even if they just publish the paper, if this is their final dissertation work, it's often a sign that, although they said every dissertation has, and lots of papers will have at the end, like future work, right? A paper that tells you future work gives you some ideas. Oddly enough, the ones that are future work are ones either they're not going to work on or they've already finished. Those are the two categories.
Usually, yeah.
So, and sort of mixed. So, could their ideas be combined with other approaches, combined with your work? This, to me, is where the real work of creative reads come in. Not what is the obvious new application of their work. What is the extension of the work? Those are things that their work alone tells you, here's an application, here's an extension. You don't have to know anything else. But what could you combine it with? Because there's literally thousands of things that can be combined with. The authors may not have thought, I'm going to combine that with that. But the most important one is, what in my work could I use their ideas from? And the less obvious those ideas are, and this is a place where it's good to spend a little bit of time. So this is why the read is so hard. Is it's not, you read the paper and it jumps out at you. This is literally spending 15, 20 minutes thinking about, what can I do with that? And, brainstorming ideas, looking at what are the subparts of your problem that can be combined with, right? The more obvious it is, the less valuable it is for you to discover it. The more you have to work at it, the more likely anyone is to have to work at it, then the less likely anyone's doing it, so it will become more publishable for you. So coming up with interesting ways of doing that. So if there were assumptions, if other assumptions were made that could improve the approach, right? Could you insert those assumptions are true for some problem? This comes back to the limitations, right? So if you found they made these assumptions, could I make those assumptions be true in my problem in some way? Right. So if they assume that there was a maximum latency between communications, well, is there a way I can ensure a maximum latency between communications? By the way, my protocol is designed, right? Or something similar to those kinds of assumptions. Are there improvements that might make important practical differences? And depending on where you're looking at, this may or may not be a big deal. But if they said, well, we're going to put these things in order and sort them, right? And the algorithm sorts, right, on a regular basis. But really all they ever need is the top 2 or 3 items. There are algorithms that will get you the K largest items in much faster time than sorting. Right? On average, with quicksort, maybe not a huge difference, but for some things, there might be other differences. Right? If they're literally using things in such a way that a cache could improve performance. It might not seem huge, but if you can get a 10% improvement in performance, would that be publishable in your space? One of the questions you want to ask yourself. And in lots of other places, are there better numerical methods, better optimization techniques than what they're using? Right? And this is a classic way, and sometimes you can easily get a 5 or 10% improvement by saying, look, they used LBGFS, which is a classic optimization. It'll optimize anything. It doesn't, not a very smart algorithm, but it's a very aggressive algorithm. It'll do all kinds of problems. But maybe if I did something else with stochastic gradient descent or some other algorithm, I might be able to get a 10 or a 30% speed improvement, which sometimes is interesting to people, right? So there's some advantages to knowing things about how to do mathematics and optimization fast, right? That maybe that's where you combine 2 papers. Well, this paper just did that technique, and it got them this kind of speed up. Could I apply that and this together to get something interesting? And then ask yourself, if you were going to start doing research from this paper, what would be the next thing you do? What's the next obvious thing to do? Put these together and start working towards them. So the creative read, I recommend you do take notes on this. And in fact, you also let the paper sit a day or 2. So you've read it, and you think about your creative read, and then schedule a little bit of time to come back to your notes and say, okay, I've thought about it on and off randomly, walking down the stairs, and cooking dinner or whatever. Right? Creative ideas are sometimes hard to force to come out of you. Right? You have to find ways of doing them. So revisit the same paper 2 or 3 times, especially if this is one where it's like, I really want to build on top of this, then you will find a way, right? You'll find some creative connection. But don't view it as, I have to do it while I'm reading, because it's just hard to force that creativity to come out. So take a break, come back to it, but schedule a time to come back and put something in your notes. So I will often put like a 2-day time frame. So.